part 2 of our video key for exam 1 for Chem 102. Oop, gotta put Bruce Banner's name up here again. Make sure you have your name on every page. Alright, now, number 4, we're being asked to calculate the density of sulfur hexafluoride at 0.32 atmospheres and 37 degrees Celsius. Now, if you look on your formula sheet, there is actually a formula for calculating the density of a gas. Density is equal to the pressure times the molar mass of the gas over the gas constant times the temperature. Alright, so we need to calculate the molar mass of sulfur hexafluoride, which we can do on the periodic table. The molar mass is equal to 146.1 grams per mole. The temperature is equal to 310 Kelvin. We always got to put our temperature in Kelvin when we're doing these kind of problems. So, density equals 0.32 atmospheres times 146.1 grams per mole divided by 0.08206 liter atmospheres over mole Kelvin times temperature. Alright, so atmospheres are canceling, moles are canceling, Kelvin is canceling. I'm left with grams per liter, which is what I want. That's a unit of density. I have two significant figures because I have two sig figs for pressure here. So I end up with 1.8 grams per liter for my density. Alright, on to number 5. We're looking for the volume in mils of sulfur dioxide. Alright, so we want volume of sulfur dioxide, shunk, that can be produced by the complete reaction of 3.82 grams of calcium sulfite with excess hydrochloric acid. And we're given the final pressure of sulfur dioxide and the final temperature. And we're also given our unbalanced equation here. Let's go ahead and balance this equation. I don't ever like unbalanced equations hanging out. Okay, so here's our strategy. This is essentially a PV equals nRT problem. PV equals nRT. We're looking for volume. We're given the pressure. We know what the gas constant is. We're given the temperature. We need to find out number of moles, and we can find that out pretty easily because we know how much calcium sulfite we start with, and we should be able, using stoichiometry and the molar mass, to calculate how many moles of sulfur dioxide we end up with. Okay, so we're going to start with 3.82 grams calcium sulfite. Use my molar mass to go from grams to moles. 120.2 grams calcium sulfite. 1 mole calcium sulfite. I'm going to use my stoichiometry. This should be balanced. I'm just going to double check. Yep, balanced. Good. All right. So now I'm in moles of calcium sulfite, but I need moles of sulfur dioxide. 1 mole calcium sulfite, 1 mole sulfur dioxide. I should get 0.0317. There's 3 sig figs, so there's 3 sig figs here. I'm going to include a non-significant digit there. Moles SO2. Alright, but again, I've marked that non-significant digit, so I know to take it out at the end. I know this only has 3 sig figs. Alright, now I'm essentially going to just calculate the volume. Volume equals nRT over P, rearrangement of this equation. So I've got 0.03178 moles times my gas constant times the temperature, 44 degrees Celsius, 317 Kelvin, right, over, what's 1.09 atmospheres. Okay, good. Atmospheres cancel, Kelvin cancels, mole cancels, liters. We should get 0.758 3 sig figs, because 3 sig figs here and 3 sig figs here. Liters. We were asked, though, for the volume in milliliters, so we have to convert this. 759 milliliters. Oh, excuse me, 758. Jeez. All right. Sorry. Now, if you got, the reason I think I wrote 759 is I was about to say, if you got 759 or 757, but your process was correct, there was probably just like a rounding error somewhere, and you should have gotten credit for that. If not, you can come in and talk to me. All right, on to the next page. So here we've got another partial pressure problem. 30 grams of argon and 15 grams of xenon are placed in a 120 ml container at 22 degrees Celsius. And we want to know what the partial pressure of xenon is. All right, well, a couple things to remember about partial pressure problems. Remember that the total pressure is always equal to the pressure of argon plus the pressure of xenon. All right, that's just what's going on there as far as pressure. But we really don't even need to think about that. We can just set this up and solve this as a straight PV equals nRT problem. All right, we can say the pressure of xenon is equal to, well, it's pressure times volume is equal to the moles of xenon times RT. You can just set that up like that. So, isolating for pressure, partial pressure xenon, PXE equals number of moles of xenon times RT over V. All right, so we've got number of moles of xenon. Now, what I'm going to do is I'm going to kind of combine this problem. You can do this in 2 steps. I'm actually going to convert grams to moles as part of setting this up. Okay, so here's what I'm going to do. Let me actually do RT first. That might make a little more sense. 8206. Again, you don't have to set it up exactly like I'm setting it up in order to get credit. All right, so 295 Kelvin is my temperature, divided by my volume, which is in liters now. We're given in mils. We got to convert to liters. 0.1200 liters. All right, now I'm going to convert from grams to moles just in this problem. 15.0 grams of xenon, that's what I have. And I'm going to divide by my molar mass of xenon, which is 131.3 grams per mole. Okay, so see what's happening here? As I'm dividing by that, look at what's happening to the units, right? I flip this fraction here. So if I were to flip this, grams would become on the denominator, and those would cancel out, leaving me with moles. Okay, which is awesome. All right, so now moles would be on the numerator. So moles actually cancel here. Grams cancel here. Liters cancel here. Kelvin cancels here. I'm left with atmospheres. 23.0 atmospheres. All right. Okay, let's look at number 7. All right, number 7, this is a Graham's law problem, an effusion problem. We're told that a sample of helium gas effused through a pinhole in 53 seconds. The same amount of an unknown gas under the same conditions effused through the pinhole in 248 seconds. And we want to know molar mass of the unknown. I'm going to call that M sub U. Okay, let's think about what Graham's law tells us. R1 over R2 equals the square root of M2 over M1. Awesome. All right, let's think more about what R means. R in this case, the rate, means the amount that's escaping over time. So it's the moles escaping over time. All right, so the rate of helium would be the moles of helium, or the millimoles as the case may be, millimoles, minimoles, that's cute, millimoles, over the time that it took. The rate of the unknown is equal to moles unknown over time for the unknown. All right. Now, it says that there's the same amount that's effusing. So these moles are the same. Moles of helium is equal to moles of unknown. All right, so let's say that we were going to put the rate of helium over the rate of the unknown. I'm just going to call that rate U. Okay? So I would have, I would have my rate of helium, moles, helium over time, helium divided by moles unknown over time unknown. All right? So if this is essentially the same, if these guys are the same, look what happens. Moles HE, time HE, right? So I'm dividing by a fraction, so I'm going to flip the fraction. All right, time unknown, moles unknown. These are the same numbers, so they cancel each other out. So the rate of helium over the rate of the unknown is actually equal to the time of the unknown over the time of helium. All right. So we also know that this is equal to, since rate of helium over rate of unknown is also equal to the square root of molar mass of unknown over molar mass of helium, this also then has to be equal to mu over mhe. Now this is not the form that you might expect, but it's because we're looking at time, just the time, not at the rates themselves, that this has changed up a little bit. Okay, so let's plug this material in. We've got our time of unknown, 248 seconds, over the time of helium, 53 seconds, equals the square root, my molar mass of the unknown, over the molar mass of helium, which is 4.0 grams per mole. All right, so we end up with, well, do all this math, 4.68 squared equals mu over 4.0 grams per mole. We end up with the molar mass of the unknown as equal to 87.6 grams per mole. Cool. All right, number 8. Name 2 ways that a real gas differs from an ideal gas. Way number 1, real gas molecules have volume. Remember, according to kinetic molecular theory, we just treat ideal gas molecules as points. They don't have volume. Second way, real gas molecules have attractive forces that must be taken into account.